I just finished your other research, the polymer one. Yeah, I think that's also. I think I announced that the Thursday class, uh, no class. I'll give you some take-home tests. So just do that as a homework. Okay. So just please wait for the instruction. And similarly for our mechanics of materials, I will give you some take-home tests. But I think I will give you I think after the class, like in Friday after the class, maybe the night. Okay, the night. Okay. Okay, so let's begin our class. So I would like to start with this review what we have in the statically determinate unit propulsion members. So the statically determinate means that all the information is given based on. So now, because we are now in the torsion, the information will be about torsion and about the inertia, okay, the diameter, and so on and so on. Okay, or torsion and angle. Okay, that's the important one. Torsion and angle, the twisted angle. Okay, so how much the deformation happens? It can be written with the angle. Okay? So the statically determinate, there will be a given information like this. Okay? We are given the torsion, and we can relate the torsion and maybe finding the deformation and finding the twisted angle. Okay? The second case is we call it statically indeterminate. Okay? It's similar to what we had before in chapter 3. We have the statically determinate and indeterminate. Before, how to solve the indeterminate is we are applying what we call the compatibility equations. Okay? Usually that equations will solve the linear solutions. Okay? Solve the linear solutions, which usually described from the geometry. So we take the geometry, the deformations, what will happen, and then we include that inside this case. Okay? That's how we solve it. And now we are moved from the elongations, the axial force. We move to torsion and rotation with angle. Okay? So the geometric will be the twisted angle, okay, for this one. Okay. Okay. Let's start reviewing this. So we have this case here. We determine the internal torques. Okay. As usual, we are starting with the free body diagram. Okay. So we slice like a slicing all this part, and then we need to find, for example, if the external torque is TA and TB, as mentioned in the picture here. So we have TA, TB. Then we need to define what will be the resisting torque, which is inside the tube. So we kind of slicing and see the resisting force or resisting torque that is going to cancel out the TA. Okay, so this is static but with torsion. So if TA is here, then T1 will be there. Okay, and then same with this one. We have TA and TB when we slice this, and we get T2. So we can have relations between these two, and at the same time, we could also look on the twisted angle. Okay? We can also write the twisted angle with this small f, which is this is the L, G, and the inertia. Okay? L, G, inertia. You could write directly with this formula or with this formula to make it more maybe easy to calculate. Maybe it's more simpler. Okay, and then we see from this part we kind of get the relations between the twisted angle for 1 and twisted angle for the material 2. Okay, so if we see from these two relations, we could also write the twisted angle for A and B based on the relations with the material 1 and 2. Okay? So A, B, C is the nodes, means the sections. 1 and 2 is the materials. Okay? So we have these two relations. Okay. So the twisted angle B is equal to twisted angle 2 is because the C is 0. Okay, now let's go to a more direct questions, typical questions for this type. Okay, so this is the questions. So you have a pretty much similar shape with the previous example. We have material 1, material 2. I think they are the same material. They have the same modulus, G, 79 GPa. They have torque in B and torque in C, which is 1,130 Newton meter and 226 Newton meter. And they have the diameter D1 and D2, and it's asking this diameter. Okay. They're asking this diameter with the information given that the shear stress allowable, that allow the maximum is 60 megapascal, and the twisted angle allowable is 0.06 radians. So this is the maximum that it can achieve. So based on this information, we can plug in all this information to the previous formula, and we need to find what's the relations between 1 and 2. Okay. Okay, we could slice this material 2 like that, and material 1 maybe here, okay, to make our FBD, free body diagram. So if we slice 1, then we get this, right? Or maybe let me write a bit more to show that this is after cutting. Okay, that's 1 and 2. Maybe let me write this is 1, this is 2, and this is the 226 Newton meter. This one is 130 Newton meter. Okay. So if we would like to know what's the internal torques in material 1, because we have the torque that is both sides going this direction, then this one here need to counter, right? Counter this two. So that will be for T1. So T1 needs to have here, okay? And then for the material 2, let's say this is after we cut and we see how it interact. This is going to be the 226, and we have here T2, right? Okay, and then what? And then for, let's say this is free body 1, or maybe let me just write below directly. The sum for the moment, okay, at the x-axis means the centroid, this one, okay, is equal 0. So we could say that since T1 is counter of the two torques, then we say T1 is, or if you would like to maybe start from, let's say taking that direction is positive, or maybe this direction positive, the same, I think, should be the same. So we could have 1130 Newton meter plus 226 Newton meter minus T1 is equal 0. So T1 is 1356 Newton meter. Okay. Let me move this to here. Okay. And from the second diagram, we get that T2 is equal to 226. Okay, and then we are going to look at the deformations. So the deformations, we write the their formula is L T or TL GI. Okay. This is pretty similar to the elongations. The elongations you have F, L, A, E, right? So L is same length, force now is torque, modulus elasticity now shear modulus, the area now the inertia. Okay. So we get the twisted angle for material 1. So T1 L1 over G, and then the inertia for 1. Okay. And then for the angle 2, then what? And then we have the limitations. We have limitations. Okay. Now, what is our goal? Our goal is to find the diameter, right? Where is the diameter? We can get the diameter from the inertia. Inertia. Okay. But how do we apply this inertia or to find the diameter? Okay. We have this two. We have this shear stress allowable, and we have the angle allowable, right? So because the allowable is 0.06 radians, so this angle, if we add, it needs to be 0.06, okay, to make sure that we get that it is on the allowable angle. So we can write the allowable for the deformations. This will be the total of the deformation by material 1 and material 2. Okay, and then we have the maximum for stress. So we can write this. The max. This is T max, right? And then R divided by the inertia. Okay. So later, because we know this, the maximum is 60 megapascal. After we get our calculations, let's say this material one, because we know all the information from the given set of problem here, then we can find the maximum, okay, the maximum for the shear stress. So let's say we take the material 1. So let's say this is the T1, and then this is d1 over 2, dr, and then divided by the inertia. And the inertia is, if you remember, inertia is pi over 2, and then r with power of 4. If it is hollow, then we need to minus the outside radius. Inside radius, outside minus inside. If it is solid, I think this is solid, right? So we can just use this for the inertia, for the polar. Then we can write so 1356 d1 over 2 is 25. And this will be pi over 2. This is also 25. Squared. Oh, 4, sorry. 4, and then we can have a cube later, right? And then this will be cancel. Let me check. Okay. Should be. Oh, wrong calculation. Sorry. Then multiply. Okay. This is, let me check, this is millimeter. This is Newton meter. This is millimeter cube. This is millimeter. Okay, check 16. Okay, 0.05052. Okay, let me write. So it should be 55. So this will be D1. D1 over 2. This is pi over 2. So this will be T1. Wait a minute, I need to check. Okay. I think we can. Over 2. Okay. So 16. So it's cancelled here. So it will be 16. And then cancel this part. Right. And then D1 cube and pi. Or here is 25 millimeter cube pi. Okay, so it should be 0.055 GPa, but I will convert into 55 MPa. Okay. And if we look at this result, it's lower than this 60. So I think it's still okay. Now do the same thing with the second shear stress, this the material 2, and we get the similar relations with different informations. So pi over 2, d2 over 2 power of 4. So we get this is 16 d2 and pi d2 cube. This is d2. So this need to be equal. This need to be equal with the allowable. So we plug in this stress 60. T2, we know the T2 is this. Okay. We put here, and then we get the diameter. Okay. So we take. Let me erase this. Okay, I think I will make this smaller. I'll put there, and I'll put this here. Okay, so we get the d2 is 16 t2 over pi with power of 1 over 3. And then we can put into your calculators. 16 multiply with 226 Newton meter. Oh, this is the stress allowable. Sorry, the stress allowable here. That is equal 26 millimeter. So this is it seems this is the solution, but then we need to also require that the twisted angle doesn't exceed the 0.06 radians, right? So we need also to check the allowable for the geometric. Okay, let me put this here. So this is D2. We need to check the twisted angle. Okay, with the same formulations we get from this part. So twisted angle 1 plus twisted angle 2. And we break down the both formula. Then we get 32. I will write directly after I break down the inertia. So 32 L1 pi g d1 with power of 4 T1 plus the second material and this would be T2. So we could have two answers, depends on what the question needs. Okay? The first answer is using the maximum stress. Okay? So we take the maximum stress and we get the diameter, we get this number. We can also get the diameter through this the angle. So using the same formula. So we put in L1, D1, we put here, and we can get D2, right? We could get this allowable by taking 0.06 radians. Okay, so this is what we call the twist angle criteria. Okay, this is twist angle criteria. While this one here, this is the maximum shear stress criteria. Okay. So if you check from here, you will get that the D2 from this criteria is 29. Okay. So to be safe, we get 26, we get 29. Then to be safe, we can just answer the D2. Possibly, it will be safe if it's 30. If the question may be asking the nearest decimal. But if the questions may be asking definitely using the maximum stress, you can just answer this, and then it's okay. It's finished. But if it's just asking like generally, then you need to also consider if we have the deformations, the twisted angle. Okay, if you haven't get your midterm, please check here. Yeah, later. Later. As I mentioned at the beginning of the class, I will give you some take-home tests. But if you get above 70, I don't think you need this additional work. Okay, so for those of you who are maybe around 50 or below 50, then perhaps this additional works can help you a little bit. Okay. So please wait the announcement. Okay. Okay. So the next section is the statically indeterminate uniform tension member. So we have this now. Let's say we have this diagram. We have material 1, material 2, similar from the previous page, and we have PA, torque, TB, and TC. And all the information is given, including the modulus, the inertia. The material 2 is twice inertia of material 1. Okay. We also have the length, and all the given information here, all is given. Okay. Okay, so what's the indeterminate means? Indeterminate means we are not sure. Okay, we are not sure. So we have we call the unknown torques exceeds the number of the equilibrium equations. It's similar to your midterm exams, number 4. You don't know the force 1, force 2, and then you need to find what's the relations. If you don't apply some assumptions, you will not be able to solve that question. So we need to solve the question through some assumptions, which is usually we are going through what we call the compatibility equations. Okay? So compatibility equations is really important, okay, to solve what we call the indeterminate case. Okay? So in the elongation, like in the chapter 3, usually if we take the elongation between wall, we can say the elongations, if you plus, it's still 0 because it doesn't break the wall, right? Because we make assumptions. Okay? So we need to make assumptions. So this is also the same. So we need also to make assumptions. Okay? Either the assumption will be in the geometric or maybe the torque itself. But I think usually both the axial forces or the torques, it will use the same assumptions, which is the geometric. Geometric. So geometric equations, okay, that will allow us to solve the problem. Okay? Because if we are not assuming or if we are not using the compatibility equations, we are going to end the problem with maybe we still need to calculate T1, T2, and we are not be able to solve the whole problem. Okay? So, need compatibility equation. How do we get that? Usually by deformation or by geometric. In your exam, the geometric is using the triangle. Ratio and triangle, right? Okay, first we could slice the models and then make the free body diagram. Okay, so slice all. So we slice. First is the fixed wall here. We slice the nodes A. Okay, to see that what will happen here. If you see A, it will also cancel by this T1, okay, to make it static, right? And then this T1 will be having the same T1 here, which also cancel by this part, and cancel also by this part. Okay, so to make sure that all the terms here are is in its static mode. Okay? All in static mode. Okay? So this is another torque here. Cancel out with this, cancel out with this, and this part also cancel out from this too, right? And then we have TC, which cancel out this part. So they are canceling in between. Okay? So we can isolate sections by sections if you would like. You can isolate section by section, but we can maybe get through for from the let's say from the B here, from the middle. So we name in B. We can see torque from material 1 and torque from material 2 is affecting by this part here, right? So we can relate that TB will have relation with the T1 and T2. Okay? So we could say we could write T1 minus TB is equal to T2, or T1 minus T2 is equal to TB. Okay, we will have a break. Okay, so let's continue. Okay, so we can isolate each node, so B and also A and C. So in A, we get the TA plus T1 is 0, or TA is negative T1. But the negative or positive later is not really that important in our process. But at the end, if we get the opposite sign, then which means it will be in the opposite direction of the rotations. Okay, so it's as simple as that, like we did in chapter 3. Okay, that we did previously. So TC here will be equal to TC. So if we take minus, so TC is equal to 2. Okay. Now from these three nodes, we get all these equations, and of course, we cannot solve this tree, okay, unless we have one more relation, okay, that will connect all these the elements. Okay. So we need to have equation from the geometric. Okay, so remember that we have T L G I, right? Or we can also write the twisted angle using the F, the small f, where F is the element force or element torque for this analysis. Okay, now the assumptions that perhaps works best, okay, in this case, in this scenario, okay, if we look at the nodes A and C, okay, if you look at the end of these two nodes, we can assume that this is the same like a wall, like we did in chapter 3, and then we assume that when we rotate, and perhaps there will be a small twisted angle between 1 and 2, or if we add the 2 in the formations, it will be equal to 0 because it's going to be fixed in between this A and C. So the rotations inside, we keep that rotations. If we plus the angle, it will be equal to 0. That's our assumption that perhaps that will be works best within this scenario. So the geometric deformation in this case, or in our words, we say this compatibility equations. This is going to be the total angle will be equal to 0. Okay, now we can also look at from this perspective the F1 T1 plus F2 T2 equal to 0. And then we can look on the informations that we have all the information are the same except that we have the material 2 is twice inertia, the inertia is twice as the material 1, right? So one material is more flexible than another one. So we could take that into our formulations. So T1, this is L, G, and then inertia, and then plus T2, this is L, this is 2GIP, okay, because the inertia is twice, and this is equal to 0. Now we can write in more detail that this will be T2 L 2 G IP. This is L or negative L G IP, and we can cancel all this immediately. So we get the T2 wait, let me calculate a little bit clearly. Okay, let me write from here to get the result. So T1, let me write here, T1 is equal TB plus 2 T2. So here, I think we can cancel this part. So T1 is negative T2 over 2. Okay. And then we input the TB plus T2 for T1, and we get that T1 will be TB over 3, and T2 is negative 2 TB over 3. Okay, so what you need to do is basically first, the step by step. Okay, as you are imagine that will be more and more problem solving. So the first thing is the free body diagrams. Okay, make the free body diagrams. Write the equilibrium. Okay, which now we are going to focus on the torsion, which is the moment. The sum of the moment need to be equal to 0. And then finding out the twist equations, okay, where the F is L over G I is the inertia. Okay, and then from there we need to make sure we know the compatibility equations. Okay, so how do we know that we need compatibility equations? We know that when we take the equilibrium if there are more than two unknown that is in the members, then perhaps we need another relations to solve that. Okay? So if here, if have, or if the equations, if equation have two unknowns or more, then we need to take the compatibility equations. Okay? So that's, you need to remember that. So compatibility, and then you can find the torques, to find the torques that you are already previously find here. So perhaps you get T1, T2, or maybe T3, you have three unknown forces, and how to relate these three. You need to find the compatibility equations, and then from there you can solve through linear equations and finding the torque. So it's pretty much the iterations. It's pretty similar to what we have, but now we change the torsion. So in chapter 3, the difference is in chapter 3 you find the force, right? You find the force F1, F2, and then you find the elongations, and then you relate those two. Now you find the torsion through the deformation, which is the twisted angle. This angle, the torque twist equations. And basically we say that this method is called the basic force method. So we focus on the force that is this element force here. There are other that we call it displacement, but basically they are the same. So I think I will just focus on this one. This displacement method, the difference is you change this into the T, and then this is going to be K, and then this will be the angle. But they're pretty much counterparts each other. So I think just focus based on this basic force method. Okay, now let's go for another example. And now we have steel and aluminum. So we have the core is steel. Okay, so it's high steel shaft, which we have the modulus of 80 GPa. I hope my writings can be read. So high steel shaft, we have the radius for the high steel shaft is 25 millimeter, and the length is 750 millimeter, sheeted over 500 millimeter. So the 500 millimeter is going to covered by aluminum. Okay, the aluminum has its own modulus 27 GPa, and then the outer radius is 38 millimeter. So it's already in radius, so we can apply directly inertia. No need to divide by 2. Nodes A and C are fixed. Okay? That's also important. So nodes A and C are fixed. Or you can see from this picture, I think easy to follow the picture. So the R inside is 25 millimeter. The R outside is 38. Okay. Nodes A and C are fixed, as you can see from the picture. It's kind of placed in between walls, right? These nodes A and C. The question is determine the maximum shear stress in steel and maximum shear stress in aluminum. And we have TA and TB as its external torques. Oh, the external torques only TB, only TB. This TA and TC are the reactions, okay? Reactions because of the torques at the nodes B. So at the beginning, as usual, we can slice all, and then make the free body diagram. Okay, how to make free body diagram? We can focus on each node. So A, B, and C. So we can slice, and then you can have 3 nodes, right? 3 nodes. Okay, let's name the steel as 1. Maybe red. So steel is 1 and the aluminum is 2. Or not aluminum, aluminum steel. Okay, steel is 1 and aluminum steel is 2. So if we look at this A, then we will get that there will be some reaction over there, which we call T1. Okay. Suppose this TA and TC is not shown in the picture. If the picture is showing you this TB, you need to look at the macro scale. Okay? So if TB is going here, then you should have reactions that is going counter the TB. Okay? So TC counter TB. Okay? Or I think it could be a reaction, or you could just make it the same with TB. It's okay. Later you'll see it will give you the same positive signs or negative sign. If it's negative, then it's opposite direction. Okay, it's as simple as that. Okay, like the chapter 3. Okay, but I think this example gave you some illustrations. All right, now we could write based on this part for node A. Or maybe let me write this a little bit down here. For node A, we have TA minus T1 is equal 0, or TA is equal T1. Okay, so this is T1, but for material 2, because material 2 has aluminum and steel, so that the torsion will have 2 type torsion. Okay, torsion for steel and torsion for aluminum. So it will be 2 and 3. So this will be 2 and 3. Okay, material 2 and 3. So how we are going to look at is, first, let's look at the node B. Node B, if we slice this, you will have the T1, right? And it will have, let's say 2 is for the steel inside the aluminum. So this will be T2. And the outside with the same direction with T2 is T3. Okay. So node B is TB plus T1. Okay, it's the same direction, and then minus T2 minus T3 equals 0. And then if you look at the node C, then we are going to see that we have the reactions from the T2, T3 from the first one. This is T2, and this will be T3. So TC plus T2 plus T3 equal to 0. I think the most important part within our calculation is this node B. Okay? Do you know why? Because we have all the necessary torques. Okay? That is going to be included in all the diagrams, which is T1, T2, and T3. So we need to find this node B. So we need to take this node B as our basis. Okay? And then we take the geometric deformations as our assumptions or our compatibility equations. Okay. Now, since we are having all the information, then we can find the element force. So the element force is equal L over G and I. We can find the inertia for material steel, right? Which is 1 and 2. So IP1 is equal to IP2, right? The diameter is 25 millimeter. So we can write pi over 2, 25 with power of 4. This will be equal 613.5 thousand. And then inertia for material 3, which is the aluminum, this will be pi over 2, 38 with power of 4 minus 25 with power of 4 millimeter with power of 4. Check just to make sure. Okay, 2,661,000. So 2 million. And then apply for each material. So we are going to take F1. F1 is 250 millimeter. And then 80 GPa, so 80,000 MPa. MPa is Newton over millimeter squared. And then the inertia is 600,000. Now this will be taken and it will be half a millimeter. So this will be It's 5.09. It's nanoradian over Newton meter. And do the same thing for the F2. The difference is the length is 500. So I will write the direct results. This will be 1.01 radian over Newton meter, or millimeter, sorry, it's millimeter. F3 is 6.96 radian over Newton millimeter. Okay, based on what we have in the picture, and because we know that the nodes A and C are fixed, so the twisted angle at A and C is 0, right? So let me write here that since nodes A and C are fixed, then twisted angle at A 0 and twisted angle at C also 0. And then from the picture here, okay, we can say that there will be a difference in between here, which means that the T1 or the angle 1, let me write here. So the angle 1 is angle A minus angle B, and then the angle 2 is angle B minus angle C, okay? And same thing for the angle 3, because they are 2 and 3 is the same in the same shape. And all the angle A and C are 0. So from this part, we can simplify that. We can say that the angle 1 is equal to the negative angle 2, and angle 3 is equal to angle 2. So by using this compatibility equations and using this F, we can find the T. So we can find T1, T2, and T3. So let me mark this is first equations. This is the second equations. So we need these two relations to calculate the torque. Okay? The torque for T1, T2, T3 using this F. We already have it here. So we can just plug in inside this one and then exchange all the, or we can start from here because this is equal to Ft, right? Ft. So we substitute F for this number, and T is T1, this is T2, this is T3, T2. So let me write here that this we can write the F1 T1 is equal negative F2 T2, and then F3 T3 is equal F2 T2. And from these equations, we can input all the necessary informations. So put here, and we get the result is T1, T2, and T3. Okay. So we need to have, so I think you could solve using some linear equations, right? So I will not complete this, but just write that from these three, at least two equations at node B and the compatibility equations, you can find all the torques. Okay, but the question is asking the maximum shear stress in steel and maximum shear stress in aluminum. So to find the maximum shear stress, I think let me add another one here. So after calculations, let me just write the result that T1 is negative 252. So this will be going to opposite directions from the one that we draw. T2 is 127. And T3 is 184. Okay. And then the maximum shear stress, remember that 1 and 2, this is steel. Just to make note that 3 is the aluminum, right? So for steel, we are going to focus on the shaft AB. So for steel, we are going to focus on the shaft AB, which means that we are going to take the tau, this is T1, and since this is the maximum value, that we need to take the absolute value here. Suppose that there are maybe negative signs within the torques. We need just the value, the absolute value. So R1 divide the inertia. So this will be equal to, if we plug in the number, 10.29 MPa. And then for the aluminum, we get T3 R3. This is the outside. And then the inertia for the element 3. Element 3, we have IP here, which is the 2600. Okay. And this will be equal to 2.64 MPa. Okay, to check whether our answer is correct or no, especially this T1, T2, T3. Okay, is this correct? So perhaps you want to know whether your answer is correct or no in the calculations. If you get some problems, you can check other nodes. Okay, check other nodes. So check nodes A and B. So check TA and TC. Okay, so check TA from here, from TA equal T1. Okay, so TA minus TC is 0, and then TC plus T2 plus T3 is also 0. Okay, now we take this sigma for the moment equals 0, and then we can take all the necessary informations from these calculations and make sure that they are equal to 0. Okay, so if they are equal to 0, then our calculation is correct. Okay. Okay, in this case, the A is negative 252.76 Newton, and TC is negative 312. Oh, sorry. Okay, and then we can see that here TC is 300. So this is to show that if the external torque is TB, the 565 Newton meter, the reactions need to counter this external torque. Okay? So at the beginning, remember, I following this book that it says that the torque TB here, TA here, TC here, right? T and TC finds out that it's negative, so it's going to be here. Okay, so that's why at the end, when we check the result, then these two are statically equilibrium with this middle torque, right? And that's why the answer is correct. So all this T1, T2, T3, the calculation is okay, because we can check that this is also true. Okay. Actually, your chapter 2 and 3, you could also do the same thing. You can check the equilibrium. Okay. If something makes the equilibrium not 0, then maybe some miscalculation in the middle, or maybe in the process. Okay, that's it for the indeterminate torsion. Okay, there is actually one section, small section about the misalignment, but I think I will skip this part. I will skip this. And then I will explain this example. This is using the displacement method, so I will just directly guide you through the examples. But perhaps they will be completed in next Friday. But you can write down the notes first, so we can directly write the solutions on Friday class. So it is a steel shaft with the modulus of 78 GPa. So steel is around 80, 100, 200 GPa. While the aluminum usually 20, 30 GPa. Okay. The B is fixed. External torque, TA is 350 Newton meter is applied. Using the displacement method, determine the angle of rotation at NA and determine the maximum stress in steel core and shear stress in the aluminum shell. So it's asking displacement method. What is displacement method? So displacement method, so in the previous way, we say the basic force method. In basic force method, we have the twist angle, right? And then F and then T, right? The F is the L, G, and inertia, right? In displacement, we are going to write down the same formula, but we are going to write in terms of T. So Ti, and now this is K, and then the twisted angle. So actually they are the same formula. Okay. So and K is G IP over L. So I hope it's still okay. So whether the question is asking, but I think the question will not ask like displacement or basic force. You can do both, okay, because they are basically the same. Okay. So first, if we look on the free body diagram first, take down here, maybe slice over there. We are going to have let's say this is TA. And since we have two material, steel and aluminum, we are going to have two torques. So let's say this is, well, maybe the inside one first. So this is so the inside one is T1 and the outside one is T2. So we can start with the T1 plus T2 is equal to TA. And then we can start finding the inertia for both materials. For the steel is the inertia solid. For the aluminum is the hollow. Okay. And I think we can continue on Friday. So I think I will end this lecture up until here. We will continue on Friday. Yeah, and I think I will skip some parts and I think we can go to the next chapter. also maybe a lot of sections that will be skipped. Okay. Because I think I will be focused more on the bending, the moment bending, the chapter 6, the beams. Okay, so I think that's for today's class. Okay.